Yeah, we will continue our models, the basic neural network models. So today we'll talk about the sequence models. Certainly, part two has a lot of sequence models in terms of large language models. But today we are talking a little bit basic concepts, which is before transformer, right? Prior to transformer, then part two we'll talk transformer, large language models, and so on. I mean, because of the popularity of GPT large language models, I'm pretty sure everybody knows what it's supposed to do, right? So, but we will go through the math anyway, just so that we set up the notations and so on, and the basics. Yeah. So basically, as we all know, like a sequence model is just predicting a sequence. Mostly we focus on text in this class, as well as nowadays in many other places, which will be sequence models, right? We will talk about the pre-transformer models, which are still useful to know, but we will go through that very quickly again, just as a background. So we do have exercise for this, but nevertheless, our focus later on will shift to transformers. RNN, LSTM, so that's the standard, especially LSTM. So that's the sequence model preferred before transformer, later replaced by transformer. Tokenization, that's something we need when we deal with text, and we will briefly talk about that. Again, we will look at coding illustrations, and you will do similar coding in Homer for this. Anyway, so that's what we are going to do today. Okay, so let's move on. So now let's think about what a sequence model is, right? So essentially, it's a probability model for sequence generation or prediction. In our case, so we can do both. Let's say we want to generate a sequence, right? Sequence is t equals 1 to t. This can be any sequence. It could be, stock price per day, right? Could be text, could be like weather and so on. But generally, we have observations, which is indexed by time t. Now, at least in this class, we are not looking at the cases where there's uneven distributed time. Basically, time is basically pretty even, which is 1, 2, 3, 4. It's not like 1.5, 1.3, and so on. So in this kind of a sequence, which is focused especially for the discrete value for this class. This class, we are looking at discrete value because those are the tokens. Those are the subject of text generation, right? So we do that. And here is the decomposition. If I have a model, right, model parameter is the data. I want to generate using this particular model in abstract terms. I want to generate this sequence. Then what do we do? We probably all know now, even you haven't learned probability because all the, when you work with LLMs and so on, you know that these generate one at a time. One of these symbol at a time. Basically, each symbol, especially in the case of text generation, it's a token, right? So you generate one token at a time, or one step at a time, basically. And then the notation really says, I want to give my model theta. It's just abstract notation. And the previously generated tokens up to t minus 1, I will generate t. And then we're starting to generate the t from 1, t equals 2, t equals 3, and so on. Just generate that one at a time. So that's essential. Yeah, basically, each term. So if you look at predicting in this particular most general formulation, you should look at the context of everything you generated before that, right? So this is essential what it is about. And then you have equation. So therefore, this generation is definitely always the precise way generate. Of course, we all know, even when you work with LM and so on, so you have a finite context length, right? So you can't just put all the history there. It can be challenged, right? So therefore, usually in the practical models, we kind of restrict the context length. It's just like what you have worked with in the LLM space. Now the questions is when we restrict context length, we instead of looking at all the tokens we look at, we just look at a part of that. So this is basically the setup. Okay. Usually when we have a fixed context length, this is called like autoregressive models. Generally, they use the previous whatever context, right? You generated up to a length of L is your context length in order to predict the new symbol, new token, and so on. They are based on the previous L generation. So essentially what we have is the following. We are generating YT based on Y1 to YT minus 1. So this is basically the setup. We basically, when we write this, we ignore the non-positive index of T minus L. For example, if there's Y0, it never come, we just ignore that. So basically, we just have a convenient notation of context size of L. For the beginning, it could be smaller than L. But in the end, it will be at most L. So this is a typical setup which we see nowadays. So overall probability now, if you use this particular model, is you do a sliding window. Each time you are trying to predict your TIS token by using the previous context up to length L. Typically, this is called the order L Markov property. In the traditional sequence modeling, L usually is small, cannot be too large. Nowadays, of course, in the large language models, this context length can be very large. We typically, at least thousands or 10,000 or 100,000, right, or even millions nowadays are possible. These were not possible traditionally. Traditionally, when you look at L, it's actually pretty small. But nevertheless, mathematically, L really impact your complexity. But on the other hand, it's convenient to use it to reduce the number of contexts. So this is basically the general way of doing this autoregressive. Now, what is when you reduce L, right? Of course, if you reduce the context length, you lose some information, right? Instead of depending on all previous tokens, you just look at the part of the tokens you are looking at. So you are using not as many information as you could, and that could be an issue in the accuracy of your model. So let's look at how do you train this model, right? When we train this model, we use the same thing as before. So before we look at the classification problem mentioned, like image classification, we use maximum likelihood estimate. Now we are considering, for example, still discrete tokens, let's say, right? It's basically you will use something like a cross entropy loss. Again, use logits is outputs, and for each of these YT, it's you draw from certain classes or vocabulary. That size typically nowadays is around maybe 100,000. It's not huge, but it's not small. But nevertheless, it's something which manageable by the current GPUs. So around that size, or yeah, so basically it's definitely more than thousands, right? So it's maybe tens of thousands, 100, or around those size. With these tokens, each time you are predicting this, but then you still use something like a cross entropy. Basically, you predict logics. Say this big K is 100,000, right? You are predicting 100,000 logics, and then you do a softmax as before, and then you use a cross entropy loss, right? In terms of your softmax, basically this becomes your model. So here is you have a model parameter. You can define neural nets, and then you can add context, and that. And this is a way generally how the transformer works, right? So essentially, later on we will talk about that, but essentially, this is basically the model. And then once you do that, you pass. You can do that with other models as well. Yeah, so basically this is essentially the setup and how do you train these kind of models. The summation here is slightly different than the before is in the image classification, you have independent samples. You are thinking the samples are just not to do with each other, right? Here is actually to do with each other because they are in a sequence, so they are dependent samples. But from formulation wise, it's very similar. You just compute the loss. Here you compute the loss, you compute the forward, compute the loss, but you have a one token at a time, and then you just sum over. So that's it. So yeah, so basically, this is a setup, and we will also come back to this later on. Assume each in the auto-regress setting, right? Assume each token generated from the previous token, L equals 1, right? That is a kind of a background mode, you sometimes call, because you just depend on context length of 1, right? This is just for illustration. And in this case, you can just form actually a table, right? So let's say you have 100,000 is your, 1,000 is too much if you do background. Maybe say 1,000 is your regular size. Then 1,000 times 1,000, you have a million size table, which you can specify this probability, and then you just count. So learning is the maximum likelihood. For example, this is a small token. Usually, sometimes you have a beginning of sentence. You don't need that, but sometimes you have that. You have an end of a sentence. You just say you're finished. You're doing that. And the second sentence is like this. If I have this sentence, right? Essentially, the background model will predict something like this guy. Right? Form all these probabilities, and then you multiply that together. So once you multiply together, then you get the probability of generating this sentence. You could generate other sentences by using the sampling, but then you essentially you give all the sentence a probability, and then you are able to sample according to that probability. So this is basically roughly that is. I mean, in the traditional setting, like this kind of setting, right? If you look at the traditional NLP machine learning doing this kind of n-gram language models as this kind of flavor, that's the one before the neuron takes over. You actually count a lot of these probabilities. Sometimes you do see unseen words or unseen something. Then you have to do so-called smoothing and so on. You have to make sure that get resolved. Those are always an issue, but in the modern days, that becomes vanishing, which we will talk about later about how the modern ways of doing that. in the tokenization. So now, today we are actually not talking too much about autoregressive model. We are more talking about so-called recurrent model, nonlinear state space model. Sometimes, if you learn time series, you have see linear state space model, but here it's nonlinear. This model are the RNNs, LSTM, the traditional before transformer. They are all recurrent models. Recurrent models, they have a advantage, which we will say immediately. Also, they have a disadvantage. But after balancing advantage and the disadvantage, nowadays they are less favored, but still they are in the basically there are still people studying that, trying to say certain recurrent models maybe can be done in such a way that it can potentially replace transformers and so on. But this is definitely a research topic. But for the traditional, let me explain. So what happens, right? So for the recurrent models, you do have unobserved states in the recurrent model, and essentially the observations are depending on these states. So recurrent has a function, right? So this one is your neural net. It's taking the current inputs, taking the previous recurrent state, get your current recurrent state. So it's always recurrently looking at the new inputs, looking at the previous state to get a new state, and then you are doing this guy. Yeah. So this is a kind of a recurrent model, and the models we talk about, RNN, LSTM, of this lecture will be recurrent models. And they have certain advantage over this kind of fixed context length, because the effective context length, one can argue it's infinite. It goes to the beginning of T=1 instead of fixed context length because of the recurrent, right? It always have a dependency. If you look at this recurrent structure, HT always depend on the X1 by using this recurrent. Yeah, and then this is your sampling. So here is the things. For the unconditional, typically what we do, we talk about unconditional, but here we actually talk a little bit about conditional. Maybe we will specify that more clearly. One unconditional generation, which is what we talked about before, right? You always set the current observation to be the previous output. You always move the previous output to the current observation, and essentially you are thinking this is a little bit like a dependency on the previous one. This one is like the background, what we talk about, except that there is a recurrent state which is maintained by the model, while in the background you just have a dependence on yt-1 with yt, but there is no recurrent state. So recurrent state is where you carry out the information throughout the time t, and therefore that gives you more information with a longer context than actually t-1. So it can be arbitrary context. Later we will show it. You can use this kind of structure with a recurrent state that can represent arbitrary autoregressive or order L as well. So this is the recurrent model. Do use this flavor of structure to simplify. Transformer has some flavor of this kind of recurrent model, except it's up to a context length. They don't have a hidden state, meaning, but here we are looking at the recurrent in terms of RN. So we'll give examples later. So here is one example, right? This is a conditional generation, which is more general when we talk about this. This is unconditional. Unconditional is actually what we talked before when we talk about this autoregressive. In the recurrent setting, you always have a recurrent states. This is learned by the model. This is not given. Why you each time you are generating next token, each time you generate next token, this one is already generated, as you know, and this is what you want to generate next. So this is what you want to predict. Basically, take this as input. You have the recurrent state, you update, and then you, this update depends on these two, right? And then you get one. And the conditional really, you'll say, I have a sequence, I have output. So basically, this is how this is generated. Yeah, so unconditional and conditional. But we can focus on this one. Yeah, this one is more popular nowadays because you, instead of encoding conditional this way, you're encoding condition as prompt, right? You just continue rewriting. So that's the current. If you do that way, you can always make this one look like a conditional, just keep generation depending your prompt. So basically, our main interest in here, but this is a more general setting. Let's basically say why recurrent will be a useful model in terms of modeling sequence and what is lacking in the autoregressive. And this is something has been discussed even now, right? We know the transformer, you have a fixed context length, and that's why people try to do the recurrence to make it better. Recurrent is always more general. Basically, it can have an infinite context length by definition. But with a specific recurrent design, you could basically you could essentially like this, right? I would say, okay, my hidden state is just a previous observation. I don't do anything. I don't want to learn this. I just record the previous as my hidden states. Then this one this one is recurrent. And you can show that. You can also show that with that you can have an F which maps h t minus one xt to yt minus one to this guy. So basically, that's from definition. The way to do that, right, is essentially shift operator. So ht, right, is basically this is t minus one have a size of L, right? It's L vector, and then you append this guy, which basically means you have L plus one vector, and then you discard the lowest, you keep the most recent L, right? So and then become this. So basically, this is a function like f. So essentially, you can write a function to take the previous history, take the current observation, and get the next history, the next hidden states by just shifting your context length by one. So essentially, this all it does is just shifting context length by one. Discard the oldest, you're adding the newest, and then this one is the recurrent. Recurrent can be more complex than this. So that's why we look at that as it's just not just mathematical say autoregressive and recurrent equivalent. They're not equivalent because autoregressive can be written as a recurrent using this, right? Using your state is your context, but not the reversal. While you have a more complex function, right? So basically, this is more general. That's why it has been in favor. We will talk about why nowadays people try to do that again. Of course, because of these slides, right? So you won't have an infinite context length. Then recurrent is always more powerful than autoregressive. But there are some challenges to that, which resolved by transformer. We hope to keep those properties, and then that's why there's current research trying to work on this. Right. So basically, this is an example. Yeah, you have history, and you're adding this. You disregard this guy. You get this guy. Okay. Let's look at the recurrent neural net now. So simple recurrent neural net, right? So what do we do? Yeah. A simple recurrent neural nets is basically this one repeats what we do. Essentially, it takes the following, right? Remember in the next token prediction, unconditional generation, this y xt minus one is yt minus two, right? It's always this one shifting by one. You always shift by one. Okay. Recurrent takes this guy and output this, right? And this is your neural net. So this is a sigmoid. This is a sigmoid, and this is basically what are your weights, right? These are like a fully connected. If you look at that, this is with a bias, and you concatenate H and X as a vector, and then you times a matrix, and you do that. And this is your recurrent. So basically, the only thing is that this one depends on previous of itself, previous version at previous token. You just recursively run this. And Y is just linear. So this becomes a logits, right? So once you have a linear, and then once you have a logits, you can do the cross entropy loss. When you have, this is your prediction, this is your truth, and you just take the loss. Okay. So I hope that's kind of clear. This is just a one layer. And basically, yeah, that's what it is. So yeah, your model parameter are these. Yeah. So I think I will shift a little bit higher of these slides. But essentially it's a pretty simple model. So if you look at that, it's the only idea here compared to the fully connected is this recurrent, right? Again, recurrent is where you are similar to the CN. You have some sort of a parameter sharing. You're depending on history using smaller number by using the CN is using this translation small window, right? Just copy each window here. It's actually one directional from left to right. You are building your history. Try to report that to Edge. So this is the model. What it looks like. Now let's take a look at how do you train that. We just have a quickly. We don't want to have putting too much math into this, but just looking at the intuition. Let's compute the loss, right? Because dependence of this guy depends on this one, right? So we know that this because of this formula, right? If you look at this formula, H depend on HT minus 1 and divide TH2. So there's a recurrent, right? So this one depend on this, depend on this, depend on this. When you take a back prop using the chain rule, right? What do? I mean, this is a loss at this particular point. You need to take a loss at all the points, right? Remember. But then let's just look at these points. These are your loss. And then you want to take a derivative here, right? And we are only interested in derivative to the parameter, not to the input. So this direction, you don't need to take derivative. Basically, you take derivative here, take derivative here, somewhere, and at some point you want to take derivative with the model parameter. But you have to take derivative for all of that. So this is each of these contains a model parameter. If you think about this linear transform W is your model parameter, you need to take with respect to that for everyone. So here is what do you do, right? So you do a derivative by prop, you do per prop, per prop, per prop, then you have that. But here actually you also need to do that here to theta. You also need to do here, theta here. What it does mean here, right? So when you look at this picture, the influence of this guy to this guy is computed by this derivative, basically, the model influence. And this derivative essentially says how this guy influenced this guy. Usually when you take this derivative, you cut off at some point. You can't just take up to the end because computation too expensive. But typically when you look at that, this is like a deep neural net in some way. Because deep neural net, you are taking layer to the previous layer to the previous layer. If you reverse that, you're thinking this is your layer, layer, right? Then this one is a bottom layer. This is a much topper layer, and then you are doing very deep up to T arbitrary large as you wish to be derivative. So this requires a big derivative, very deep, like very deep neural nets, behave like very deep neural nets in terms of derivative. So because of this, yeah, it's a clear one. Just from mathematically, when you say I want to do backpropagation to train the model, the behavior is like very deep net. It's one layer per time step, right? So gradient flow back to earlier stage, finally to parameter data. And this one can be anything here. And you have to sum all this up. All the layers share the parameter, right? They have identical parameter according to the recurrent. So essentially, you take parameter with respect to all. Now, this is a key part, which actually make it less popular now. And what people need to, if they want to do a very complex recurrent model, what they need to do is parallelizable because of this structure. Yeah, you have a key, you have to do one at a time. You can't just do parallel compute all these simultaneous, because this one depends on this guy. So you have to depend on everything this. So if you have say 1,000,000 token, right? Or 1,000 token, then it's like 1,000. You have to take back 1,000 times. It's like 1,000 layer neural net, which is expensive. This one is key bottleneck. Turns out this one cannot be developed unless you solve that. But with now try to make a recurrent algebraic simple mathematically, you could do parallel for certain, right? We will not go over that, but basically why it's become unpopular, why transformer doesn't have this problem, we will talk about that. The computational cost, this one is not larger. It just they cannot parallel. We need the parallels to train the models. So that's the key part. And yeah, and then this but I think this has some of these desirable property. Multi-layer RNN, right? So you can do this multi-layer. This is no problem. Essentially, what you can do is you just stack this together. I think just instead of up to original this guy, you up to this guy, and then you have another this one treating as input, right? So you can just write to yourself, and then you basically. So this is not too much. Here is an example RNN. You don't need to write all this recurrent code because this already given. So what we have is already given recurrent inputs, right, and hidden number of layers even, right? Number of layers could be 2, right? 2 is just like what we show. 1 is what we studied before. But if you're 2 layers, it's just like what we see there. Hidden size is edge, the size of edge, right? So you have to pick one, and that's about it. Yeah. Forward, you can do this. This one is at each position x. Yeah, basically, x is this shape, right? And then you do that. This, typically, what's interesting about RNN, so for the other things, right? Let's say for the CNN, right? They don't have self-recurrent. Therefore, training and test will be similar. You don't need to write it differently. But here, what happens is this is useful for training. Training, we will see that you actually shift by 1 the inputs x, and just like what we show in the formula. So you just shift by 1 your inputs and target, but they are the same. For the test, because you need to feel x is not known, right? You have to 1 at a time. So you have to do a slightly different. You have to generate 1 at a time. You have to generate 1 at a time. So we'll come to that later. But basically, this one is suitable for training with a suitable x, which we will talk about. And this is a part of you probably want to understand. It's kind of useful. I mean, we don't need to write this code, right? This code is already being written. So this is not something we need to write. But for here is something we want to understand. The training and the type generation are slightly different. Forward is you can always use that for training, because when people do backward, right? So they first take the forward and then do the backward. So this one is suitable for training, but not suitable for generation. Because you cannot give X. Okay. Yeah, I think there's just a remark. The output is the same as it's a hidden states. So basically, this is just hidden states, right? It's just the output. Then this one is the next layer, the next layer, the linear layer, make it the logits. Right? This output hidden to linear make logits. And for the logits, you are changing the hidden layer, hidden size. In this particular, actually, I don't know what is said here, is hidden size to the number of vocabularies. Right? The output, the logits should be the number of vocabulary. Okay. Okay, so let's look at these. So we want to go through the other recurrent models. So this is roughly what we do. And you should understand that there's a backpropagation through time, the concept, and why it can be slow, right? You should also understand that there's equivalence to the deeper neural nets, right? And there's a forward is just like this kind of a recurrent structure. One thing about the deeper neural net, we talked about in the last few lectures, and there are solutions to that, right? It's a vanishing gradient, right? So this is essentially the thing which matters. And vanishing gradient will be a problem in the recurrent. You just forget a lot of earlier steps, right? It cannot be memorized. After 1,000 steps, you forget. Which is not unreasonable in some sense. You can think this, but usually when you don't careful, this one can forget much faster, right? Maybe 100 steps or even 10 steps you can forget. So you need to do something to make it remember, right? This is vanishing, and that could be blow-ups. Blow-up is oscillation, but we are more focusing on this guy. Blow-ups, if you are not careful for a dynamic system, it can happen as well. We try to more focusing on this. This one, there are some other ways to treat. For the vanishing gradient, what do we do, right? Recall that when we have talked about vanishing gradients techniques before, right? So if you think about that, we have some optimization techniques to do that, right? We have the optimization is paragraph. Right, so if you recall, we are talking about something which is related, not quite exactly solving that, but quite related is this normalization batch norm, because that's covariance shifts. If it shifts to the zero part of your activation function, you basically certainly you have more vanishing gradient due to zero, right? So we have talked about another structure which turns out to be important. It's a ResNet structure, right? Residual structure that is trying to bypass the NN part of the gradient. You have identical, which make it much easier to propagate the gradient. So they have a so-called skin connection or residual connection, whatever. But essentially, LSN turns out to be much earlier than ResNet. They later also have a version for CN as well, but have a similar idea of LSTM. But essentially, they are looking at the same issue. So long short memory. Basically, the memory get preserved. In the recurrent model, essentially gradient vanishing means you forget history, right? You don't want to forget history. You have a long-term memory, and that is the LSTM. Basically, this one sounds like very similar to the ResNet. Turns out that there are some very much similarity here, and you want to have a special cell. This cell will have long-term memory, and this cell will be. This is like a residual, right? This is looks like. if you have this shell, this one is the residual, and then but you know they do not use a residual. they use gating. Gating is also a very smart and highly used technique, even in the modern designs for others like picture experts and so on. So essentially, this is a little bit beyond the residual. This is a residual, right? We see that before. And this one is a gated, you can argue, plus this. But if a gating is nicely to be one, let's assume, right? Let's say you have a gate, it's a learnable gate. If let's say this is a one, what happens, right? What happens like residual? Residual, then you have this bypass path to get your gradients. So basically, the gradient of this one can be propagated much further. This is just why they have so-called long short-term. You want some short-term memory to reflect your inputs. You want a long-term memory to remember the history context. Basically, you can think about a summary of the history, right? So yeah. So essentially, this is what it does. Yeah, it just have a more complex structure than the residual by using a gating. And in the recurrent, that's basically what people use. Gating is something pretty popular. Again, it's also used in other contexts, not only the recurrent URLs. Here are the equations we could get, right? So this is so-called forget. Remember, we have a forget gate is hopefully if it's one, right? If it's one, it's a residual net. It's like becomes residual. But this is learnable. All it says each time you always take the x, your hidden states, right? And then you get the forget. And this guy is called the input gates. It just control how much input. We will see later. This guy the output. So they have a lot of gates. You have input, you have output, you have forget gates. But forget gates is main. This one is just say control the influence each input, each output, and so on. But this one is a key control about how that memorized across time history. So this one is the current gate, which is yeah, basically it's a gate context, and then basically this one is something like that. So they update the gates, but then they want to use you can think about that as a residual, but allowed to forget. It's a more flexible residual structure, right? So that the yeah.
Is the forget gate basically like an attention for previous states, like to see?
It's kind of it's not attention, but it's kind of determined by the states to say whether I want to remember each particular, because each state is a vector, right? Each particular element of that vector, should I forget that? Should I keep that? Keep that, I will have f equals 1, right? It's like residual net. Forget that, I will say 0, and you can do in between. So it's just more flexible. Hopefully you can learn that. It's a more flexible residual network. And it's not attention, but it's a kind of keeping the history. Attention is more direct way of just say to attend to the specific history. But this one, you can, presumably if everything is 1, right, you can actually go arbitrarily long before, right? You can, this one will be linear growth in if you have 1, right? This one is a linear growth, but then it's arbitrarily, you can go ahead to even the beginning of T. So it's much longer than your context length, typical. This one, you know, you just say, okay, this is a hidden state. You can, yeah, you can say this is a slow memory. This is a faster memory, right? So, and then you are basically, yeah, basically this model parameter, this output. You do another one, and this is let's see where is input? Yeah, input is coming. These two, yeah, I'm not sure. So these two, they is doing here. And there are simplified notations later on. We will see make it much simpler. But basically, this is the original one. It's widely used. People tend not to modify that. Turns out that people could, right, just play around with what is useful, what is not, right? But usually people don't, just treating it as a standard neural net units. The only the well-known modification is the GRU, which we'll say a bit. These are complex equations. Nobody remembers that. To be honest, you just need to, once you need to understand what it actually try to do. That's all, right? Because you can write other equations as well. Yeah, I'm not entirely sure this has to be this way. This is not say this is not Bible, so have to say, oh, this is just the things you need to be this way. I mean, it just they have a design choice, but people don't interesting people don't try to mess up with this. So it works well. We want to say, but this one is pretty much get to the long-term memory. So just want to make sure you understand, right? But this controllable. So that's all. Yeah, the other one you just say whether it should forget or should be whatever. Just different gates, the design choice. Right. So this turns out to be much better than RNN in terms of forgetting RNN. You will not be able to remember things because of the gradient decay. This guy will. So because of this residual extra, but it allows forget something. Basically, okay, it's different than the residual in the sense of if something I shouldn't actually remember, I will forget. So that's whole thing. Yeah, this is just a graphical drawing, just more illustration, which we don't have to do. Okay, so basically that's all. Again, for the writing, we will not ask you to write this LSTM cells one by one. This is enough for you to know, right? So basically, you say, oh, I can write RNN. If I run the LSTM, that's it. Yeah, this is it. Yeah. So you have input size, hidden size. We know number of layers, and typical cache force is true, and basically, this is like RNN, except you replace RNN by LSTM, right? Remember, LSTM have a cell and a hidden state, but eventually output will be look at the hidden states. Hidden states which generate logics. Generally, the hidden state itself bypass fully connected. It gets to the logics. Logics you can calculate the cross entry. And that's all. Okay. I hope this code is clear and simple. Again, this one is suitable for training because in the test time, if you generate token one by one, X as a sequence now no, so you have to do that one by one. You cannot just in patch. But here in the training, X is shifted Y. Well, actually, yeah, and then you basically knows that. So yeah, so basically, this is the same. You just replace RN by LSTM, nothing new. And this is the level what we know in this class. Here is, as I mentioned, people usually don't mess up with LSTM. This is the one which the most notable playing around with this, try to simplify, right? So what do they do, right? So you can think about that. What they do, right? This one certainly should be there. We know that this guy should be there, right? It just, do we need to, right? Input and forget. You just say, no, we don't need to input and forget. We just need to forget and 1 minus forget. You either remember this guy or remember the new one, right? So that's why, say the input, whatever you could mess up. And the other thing is, do we need a cell and really cell and edge, right? Say, no, we don't need that. We just need an edge, right? So basically, to simplify. No cell, right? Essentially just an edge. This one calls you the residual-like structure called update gate, but essentially it's behave the way like a forget gate, right? So it's a like. It's just a little bit more rigid in the sense of they are not a residual. It's always moving average in some. The nice thing about moving average versus a residual, you can argue is a way of is this. The range is always controlled, right? If you're residual, you can grow the range, right? So basically, each previous plus other thing. Even the plus other thing is 1 between 0, 1 or minus 1, 1, it could potentially grow linearity. But here is controlled. So that's these are all design choices. And this, yeah, this one is typical. So this one, and then basically this is behaves like this output gate, right? Output gate, but then you're using output gate because at each time you keep a lot of history. Some may be irrelevant for the current generation. So the output gate, you try to say which one the history should be irrelevant for the current generation, which is you just keep for summary purpose, right? Not for the duration. So you do that, and then once you do that, that's it. Okay. So this is a simplified structure, and GRU is that. Okay. So essentially, yeah. Okay, they are pretty much the same. So I don't think there's much difference than this three code. So you look at the one code, you just replace RN to LSTM, LSTM to GRU, and everything else keep the same. Okay, so yeah, so that's about it. We will quickly say it's not basically it's not a golden standard for LSTM. All the people try not to mess up with that, but here is one example. It's been changed and it also has been used. I think these are all the same comments. Just mentioning the output is hidden. You want to make it to be output, you have to go through a linear. You have to go linear. For example, even the dimension may not match, right? Hidden is hidden. Output will be the vocabulary size. Here, actually, vocabulary size is 1. Maybe I should make it not 1, 16 or something. Just make it more immediate. Tokenization. So now, once we have this, we can use this to do text generation, right? So that's our next topic. If we say, okay, we want to do that for text generation, what do we need to do? First, we need to do is understand it's a so-called tokenization. So this which we'll talk about. And after that, we piece together, we will do text generation. Tokenization. So in natural language generation, right, we generate a string. Essentially, it's an arbitrary string. You can be whatever it is. Also, whatever in different languages. Yeah, it's can be in Unicode, but for now we look at the ASCII code. So one approach is this, right? This one basically says we generate 1 character at a time. There are 2 approaches actually. You generate the traditional, a lot of generate 1 word at a time. But if you generate 1 word at a time, that could becomes a problem because it could probably you can only generate non-English words, right? If they have a new words, then it can be in trouble. Another one, if they say, okay, I don't want to generate 1 word at a time because you have unknown words, then I can generate 1 character. This always works, right? Generate 1 character always works. Because it's just a character. Everything can be composed into character or Unicode, whatever. The problem is that one just too slow. People don't do that nowadays, right? So if you look at large language models, they don't generate 1 character at a time. You generate a sequence of tokens. Basically, token is a consecutively, very frequently occurring consecutive sequence of characters. It doesn't have to have a semantic meaning, but hopefully they carry out some structure, which is correlated to semantic meaning. But it doesn't need to be say, oh, this one is grammatically should be this way. They don't say that. Essentially, they all be done automatically. They are by programs to generate these tokens, summarized by looking at the frequent sequences in these characters, and so on. So instead of generate one character at a time, we generate 1 token. Right. So this I want to clarify first is you need to generate one token at a time. Token maps a character into a sequence of token IDs. And what actually the LSTM, whatever the RNN they are working with as input are integers. They are not taking strings as inputs. They're taking integers and map out integer like a class, vocabulary. So it's an integer from 1 to 50,000, for example, if that's what your vocabulary size. And you want to map these tokens, right, corresponding to this index. So these are indices, integer indices. And then for each one of that, you have a token, have a string representation. Basically, when you're decoding, you generate a sequence of tokens. You just map these tokens into the integer sequence into a string. For string, you also map that into a integer. So essentially, tokenization is mapping a string. Encoding is mapping a string to an integer sequence, where when you have a tokenization decoding, is mapping this integer string, arbitrary integer string, into a string, into basically a string. So encoding maps text to IDs, and decoding maps IDs back to text. That's why we want to use token. Basically, each token can be multiple characters, right? Not only one characters. You have a shorter sequence, better structure. If we look at the cost of LLM, right? They are not counting characters because that's not at the model level. Turning token the characters were cheap, but each time the actual cost is generated tokens, the integers, right? So basically, you always token counts. So not so if you have a very large vocabulary, you use fewer tokens. The context size of say token size of context size of 1,000 could be say 3,000 or 4,000 characters. All right, so you're expanding your context size for free because of that. So basically, shorter sequence is a better structure. And there's a better structure because of this tokenization. You can take advantage of that. Here is the tokenizer. Usually, your traditional NLP, your word tokenizer, as I mentioned, each word is a token. Usually, word should be token because they are frequent. You see in the English text at least, right? So all these words generate tokens. But before this one, you have to do more, right? One limitation of the word token we mentioned is unknown word. So people don't do that, just using word tokens. What do you use a subword token? For example, this one be a token, but both this and this can also be a token. And all the characters also need to be a token. So essentially, this token can overlap. It doesn't have to be unique in some way. And you have a tokenizer. You can instead of a tokenizer to be this, you can tokenize to be a smaller units. And mostly popular. I mean, there are few things. I think there are discussion about which one is better in some way, but usually any of that you pick is sufficient. We will do this because this is GPT-2. We probably do some examples GPT-2, and those are the using BP. But the details doesn't matter. Essentially, given text, they will after this tokenization, right? You call this tokenizer, they will generate an integer sequence. Given any integer sequence within the vocabulary size, they will generate a text. So basically, there's a two-way map. Yeah. Also, they don't have unknown words in this particular tokenization because they all include all the characters as basic units. So all characters can be produced. Therefore, they can be arbitrary text. They can be even different languages or whatever. So they can all be tokenized. Okay. So this is tokenization. Essentially, just map string to text to integer and integer to string. So that's how it is. Here is what we will use later on, and we will also use that here for the generation because it's just convenient. This one can be used together with GPT-2. Later, we will talk about that in the part 2 of the class, right? We will looking at the large language models. Of course, we have limited computation, so only thing we probably can play with is GPT-2, not the larger models. But nevertheless, for the tokenization, they have a tokenization, right? It's a BPE tokenization for the GPT-2. You basically using the Hugging Face tokenizer, you just import this tokenizer, and this tokenizer is your GPT-2, and then say basically, okay, here is what you do, right? So and then you tokenize the sentence, right? These tokens will be tokenizer and tokenize this sentence, and after that you get your tokens. Tokens are the integers, right? So and token IDs you can predict basically IDs. So that this is basically what it looks like. It's a basically some sequence. And then you basically decode the string, right? So for example, this tokens is this guy. This is a space. This thing in the GPT-2 tokenizer is a represented space. Okay, just a visual representation. And the tokenizer they just string. So they just illustrate. Go back. Token embedding. So once you have that, there is something called the embedding layer, which maps the discrete into logit to discrete, right? You can think you just sampling. You have a cross entropy loss and so on, right? Embedding is reverse. You have a discrete into a continuous. Usually what it does is a so-called embedding layer, which basically is essentially a matrix. You have any vocabulary, any integer, you map to a number of embedding dimensions. And this can be learned. Basically, this is just a linear layer, special linear layer taking sparse inputs about the, for example, for vocabulary size, if your embedding dimension is 64, vocabulary size 50,000, then it's a 64 by 50,000 matrix, but it's sparse because you're taking one token, one of these rows matters at each time. So you just each time you're taking look at the table and you just get. So it's not a it's a linear with a sparse input. One hot basically So and you can learn this token. There are some nice property of this embedding texture. We will not go over about embedding, but essentially this is just the input layer in our you're always embedding for LSTM text, for transformer, whatever. They are always embedded. Okay, so here now once you put that together, first you need to tokenize, right? Remember your first tokenize, you know for this model always treat it as integer. You always integer in, integer out. You don't deal with strings. The string is dealt by tokenizer, not by the model. Okay. So model, but you have an integer string, right? So first you always have an embedding layer. This is a learnable embedding, and the LSTM, and then FC, right? So and then that's all. Oh, there's a number of layers, which says you do number of layers of LSTM. Basically, forward. This is the number of layers. I mentioned. So you can do more than one layer of LSTM and hidden dimension. So embedding first, when you do the forward, again, this is useful for training, right? Not for testing. Testing we'll talk about soon. And output is your LSTM. It could be multiple layers, but in the end, output is your hidden space size, hidden dimension size. You go through FC, to get your output. At this point, you find the logits. Logits, you can compute the probability. Probability can do sampling or doing the loss calculation. So that's training. Right, this is training. Training does the following. So you let's work out this. The example also is given. So you have that. I think the exercise I will do something like probably pretty much similar. In the homework. We'll do some training, but using slightly different, just different parameter setting, different whatever. So this is a cross entropy, right? So not surprising, each token, and this is the model, text generator, and you have populator size or whatever. So and the optimizer is add-on, right? So that's we do. And hidden is you first need to initialize your hidden. So so this is what you usually do that. And then this guy, we will talk about that later, or you can look about it. But essentially, you're getting X and Y. This data loader will take the X and the Y, basically the shift version of each other. Why is that? Because you are doing next token prediction. You always stack together by shifting one. Okay, Y is always one token ahead in the future. X is always the previous one, right? So you're shifting this. You're getting a batch of a sequence, truncated at a certain length. And then basically, this is standard, and this is this model, right? So this is init model, and this is doing forward. And then this loss calculation. So loss calculation, and then that's about it. The part of basically this is the main part of this hidden is the first hidden states need to be initialized somehow. So I just want to say, I mean, then it will get bad propagate, right? Because it will always depend on the previous hidden state, always your previous hidden state of particular units. So you need to initial some hidden at some point, right? In order to actually to carry out a recursion. So this is why you have hidden state happening there. It's really saying you have to initial it to be initialized. And you always use the same thing. Right? So this is a training, and then basically do calculation, and we will. I don't think we have this loader. Maybe I will see if we have a loader, but the generation is a little different. So that's one thing which is different from sequence versus the earlier like classification and so on. Right. This one has to generate one by one. You generate up to certain line. Right. Temperature is another thing which we will talk about. So this one basically says I generate one token at a time. It's not like I'm generating the whole sequence. Basically, this essentially each time you want to compute the next token, right? So basically, you have output with one hidden with current inputs, and then you are generating next token. This one we are sampling. Softmax, remember, is what we do the logics, right? Softmax. There actually needs to be, here is the temperature, right? Temperature is, this is supposed to be the logic, right? Temperature smaller 0 make logics larger. So what happens to make logics larger? If you go through the softmax, you think about that. Larger logics actually more deterministic, because one, if they have a smaller difference, enlarge that difference, they stand out, that big one. If something is large, become larger, and you take an exponential. So this one makes a sharper distribution, more deterministic. 0.1 is magic number a lot of people use, even for the LLMs. Training is always one. Temperature, in the training, you always use the logics. In the generation, sometimes you generate less random text. You use smaller, which is more deterministic text. 0.7 is a number a lot of people use. And then, probability is this guy. It's already sharpened by the temperature. Your probability now is where you use the sum. It's called the multinomial. But I know basically sampling the according to this probability. Essentially, you're sampling according to probability, picking one token, which is an integer, right? Up to your vocabulary size from this probability. And then you append this guy, then basically, basically you're doing essentially you are actually you're repeating this, right? So basically, yeah, you're you basically you're basically repeating this one. So this one treating, if you look at the input, this one is always treating this as a size of one, right? So the input. Basically, input size of one means you just look at one token at a time. So this is first generated becomes the next input, right? This one, just one token. This token will go back to that with update the hidden and update token. So it's always basically always one unit at a time. When you do training, you do all at a time, but when you do the testing, it's always one at a time. This one looking at if you look at this code, what it does is just one at a time, one token at a time, and the input is also the same. It's a one token at a time. Okay. So that's about it. Then that's an example. So yeah. So basically, you just generate. This is a trained LSTM. The code is there. So code is available, which you can take a look. There's a prompt and the generate token. You can generate multiple ones. This one generated. This one actually is a little bit better one. So you can look at the examples there. They are generating more strange, but somehow they do see this book of basically Alice in Adventures in Wonderland. Also, I think I should probably put in the slide, but I didn't. But that's in the code is the data load. The data loader, after you get in the batch, you specifically you should look at that because specifically you are shifting the input and the sentence by one. So that is just forming the tree, X and Y, right? So I think I probably should put that in the slides. I'll update slides, just put that in, just so you're aware of that. Yeah, but basically, it means the small text, the small model, it just sounds like in that style. So that's essential. What it looks like. Just stylish, but it's not in a. It's still broken, right? It's not in a, good, but nevertheless, it shows that. I think last we want to say a bit about remarks. This one just give a quick introduction. How do you set up text generation, which will be useful later on when we do the LLMs, right? But this is a pre-LLM models, which still matters. Even nowadays, people try to work with these models, hopefully using that to improve a transformer, right? So that's definitely the research direction. A lot of people are interested. For the reason they can remember longer than the context length, while transformer just a cutoff. There's no way you can remember long. Now pros, they can generate model infinity by recurrent. There are definitely forgetting issues, and LSTM and GRU try to resolve that issues. Decoding is linear in sequence length because it's one at a time. Training is also not parallelizable. That could be an issue, right? Cannot be parallelized. So that's the killer of these models. And unlike transformer you can parallel. So that's why being adopted. There are also other nice properties. They scale well. Another thing about transformers, people notice they scale well. When model size become larger, the performance also scales. Not every model is like. If you look at some CNN, look at some, they don't. Due to implementation through time, but this is parallelized, right? So can be challenging to scale to large models, and both for training and for other issues. So this is still currently a lot of research, but to put in the historical context, I think it's good to use these examples just to show the whole pipeline about text generation. Okay, and which we will later use. So that's all. Okay, so these are the references if you're interested, or just look at the slides and so on. Okay, we are done. Question or?